Hello. Good morning, Sasi. How are you?
Yeah, hi. Hello.
Uh, I
Hi,
think
Samajit.
it is around 5 o'clock there, right?
Yeah, it's like 5:28 as of now. Yeah, can I just share the PPT once so that I can
Uh,
see if
yes, yes, we can just taste it once. Let me stop sharing. Hi, Aman. Can you please go on mute?
uh, is it
Yes.
fine?
Yeah, yes, yes, yes.
Okay,
So we'll wait for 2 minutes. Then,
sure. Do you need the camera to be switched on or like it's fine?
it's fine. Fine. I'm not interested.
Okay. Please let me know whenever I have to start.
Yes, yes, yes. We can. Okay. So good afternoon, everyone, and good morning, Sasi. So we
Good
are
morning.
extremely thankful for joining so early, so around 5:30 a.m. in the morning in the time now.
Yeah.
So a brief background of Sasi. Sasi is currently part of CSI or CSIO Chandigarh. So Sasi is a postdoctoral fellow in the Department of Mechanical and Aerospace Engineering at University of Buffalo, New York. His current research area is optimal state estimation for vision-based navigation of autonomous vehicles. In the past, he has done his PhD from Academic Scientific and Industrial Research (ACSIR) in the area of navigation and control. So his major interest area and research work is in the area of image processing, computer vision, artificial intelligence, and optimization algorithms, in which he has also done a lot of contribution in the research findings, and he has many more work in that area. So without much time, I will request Sasi to kindly share his views on this topic and address this gathering. And I hope all the participants will gain some knowledge out of it. And we'll take the question answer at the end of the session. Uh, will that be okay, Sasi?
Yeah, that is completely fine.
Okay, thank you. Sasi, this is all yours, so you can start the presentation.
Okay. Yeah. So, a very good afternoon to one and all. Thank you, Dr. Pradhan and Samarjit, for inviting me for this lecture. It's a nice experience actually to prepare the PPT and actually deliver it at this time, but it's nice. First of all, thank you all the participants as well, for listening to this. And do let me know if you have any doubts in the middle. I have prepared the presentation in three parts basically, or basically you can say two parts. The first part will basically try to cover how the image processing fundamentals can help us in leading to vision-based navigation for autonomous vehicles. So now let me just start with the presentation. So before we go ahead, first let me just tell you that I'll first uh, is somebody's microphone on? Can you just please see that? I hear some disturbance. Yeah, all set. So fine. So we have some camera fundamentals, that is pinhole model calibration and transformation. And the second part of it will be covering the feature detection and matching part. So these two basic parts will be used in the vision-based navigation. So the first thing is like how the sensors in the camera capture the analog signal and convert it into a format which can be seen by our display systems, whether it is our mobile phone or whether it is a television. So we have the analog sensors camera, either CCD or CMOS, which is then converted into some specific format, either NTSC or PAL, or depending on what kind of camera we are using. It is then digitized and then it is provided into a monitor or display. This is a basic pinhole model. The basic pinhole model, you will see that you have a world point that is XYZ and the image point as XYF. So if we apply the similar triangles principle, we can see that the image point can be represented as Fx by Z and Fy by Z. And so this is basically in homogeneous form. When we go in the homogeneous form, we can also represent it as X is equal to Px, where P is our camera matrix. I'll come to this P matrix after one slide. But before that, let's discuss what is in the camera calibration. You would have heard many a times like camera is calibrated. Oh, why do we need to calibrate a camera? We need to calibrate a camera because many a times the pixels that seem to be square in nature is not really in that shape. There are many a times like a pixel is 2.2 microns by 2.3 microns. So like you will find that the number of pixels or the length of the pixels are not same in both the sides. Similarly, the number of pixels in the horizontal side is not same as the number of pixels in the vertical side. So we need to have unequal scale factor for each direction. And then also that there are something called as a skew factor, and the camera is not always aligned to the center of the coordinate frame. So these few things lead up to the calibration matrix, and a calibration matrix is like or a camera matrix also called. Now this calibration matrix is the camera matrix which helps and it is in mapping the world 3D world point to an image point. And so this is the matrix over here, that if we have the 3D point shown here as xs, ys and zs, this is the 3D point and this is the 2D point. So we can map it from 3D to 2D. And when we have the scaling parameter in both the x's, in x and y, we have alpha x and alpha y. This s is the skew parameter and the x naught, y naught is the coordinate of image center in pixels. So this particular matrix is called as camera calibration matrix or K matrix. So these are the internal camera metrics parameters. Now there is something called as external camera metrics parameters. What external camera parameter does it is like it stands from the 3D point to a 2D point, like a 3D world frame to a 3D camera frame. And how it happens is like we have a 3D point, 3D coordinate frame xs, ys, zs all in capital on the right, and on the left we have the camera coordinate frames. So we need to transform with the help of a rotation and a translation from this coordinate frame to the other coordinate frame. This r here is rotation, this minus rc is the translation. I have also mentioned it here. So there is a good proof of how the translation can be written as minus r into c tilde. The c tilde is basically the center of the camera in like center of the camera in this frame. And so now how like translation is generally easy to find, like it's already 3 axis translation, txt by tz. But for a rotation to represent mathematically, we have matrices like rz, ry, and rx. So if you these are the three matrices, and how these matrices have evolved here is like we have a point x y z here, and if we at an angle of theta, considering it only for two axes, so when we rotate it by an angle of phi, we can write the new x dash and y dash as r of cos theta plus phi and r of sin theta plus phi. And when we substitute 1 and 2, we can write x dash y z z z in this form. And when we have the matrices for all the three axes, we can multiply and eventually obtain the lower part of the equation. So now this was the part of a brief about the camera calibration, which is very, very essential before we start working with any image processing related activity, especially related to computer vision. The second part is the feature detection and matching. In feature detection, we have different kinds of features. Features are either single scale or multi-scale. So now let us consider that we have two images, like one on the scene. There are two sets of images. The one on the left is like two images in which there are, you may see that these two images are more or less related, but they are not same. So the task was to do a image stitching. Now, if we need to do image stitching, that means that if we are able to find those portions of the image which are similar to the second image on the left, we can like align them together and we can make a bigger picture of the whole image. So what is done is like the features are detected first in both the upper and the lower images, and then a correspondence of images are found, of the feature points are found, that like how the image on the left or the feature on the left is matched to the feature on the right. And once that correspondence is found, we can use it to align the image, and then you can see the image which was small has now been stitched to provide a better or holistic view of two different images together. So we are able to improve the information content by kind of, you can say, adding, but it's not actually adding, but it's actually aligning and stitching the images. This kind of feature matching activities are used in several applications like image alignment, 3D reconstruction, motion tracking, object recognition, indexing and database retrieval, and robot navigation. So what are the features of a feature? A feature need to be like the first I have what we have experienced is like it should always be unique, or it should be basically mm I mean to say, if we are representing one feature, it should represent that particular feature itself. Now, if you see in the previous slide, this particular feature can be matched to 4 different features here, but that should not be the case. A good feature should always match with only one unique feature on the right hand side. So and the other some features are, it's like it should be robust, and it should be able to detect same feature in case of any transformation. Like if we are making a rotation or a translation, it should still be able to match the same feature. It should be repeatable. That is, even if I am changing the orientation of the feature of the image, it should still be able to detect the same feature. It should be accurate. It could be used, it should be able to be used for any different application, whether it is for image stitching or whether it is for like any other image processing application. And a few others like efficiency and quantity. Now I'll just go with few like 2 single scale detectors and 2 multi-scale detectors to just give you a brief overview of how and what a feature detector is. So like the single scale detectors, like if somebody is working in this field, they would know that this is a like Moravec detector. Moravec detector basically is called as a corner detector. What it does is like it just tries to obtain the like you can say the gradient of the image in particular direction. And when we try if you have a small portion of the image which is either completely black or completely white, we can say it's a flat region. And if we have a edge, you can see in the middle image how the edge look like, and a corner, has like some isolated points, and this is the way how we detect a corner. But Moravec detector was like in 1970s, but now it's not being used much. However, we have something called as Harris detector, which is still very popular for its for the reason that it is able to provide a different type of mathematical corner response. Now, if we have the sure, this is visible nicely, but like if you see here, the M matrix here, it is computed as a gradient of an image in X direction and Y direction on the diagonal side, and on the off diagonal elements you have IXIY and IXIY both as the multiplication of image gradient in X and Y. So if we take the determinant and trace of this matrix, we can find a measure of corner response. This R is able to, like if we find out the trace of eigenvalue of this r by r, or the eigenvalue of this M matrix, then in that case, if the eigenvalues are large, it means it's a corner. If it is small, it means a flat region, and if it is negative with a large magnitude, it's an edge. So this way we do not have to visualize, but we can compute mathematically how whether a particular region is a corner, edge, or a flat. So this way, Harris detector has been very popular and still used widely. Further, it is very simple to compute as compared to the other detectors, which I will discuss in the next two slides. Now, this is Laplacian of Gaussian. So this Moravec, Harris, FAST, or some other detectors, these are all single scale detectors. What it means is like if we have an image of 100 by 100, we do not scale down it to 50 by 50 or 25 by 25, or take it up by 200 by 200 or a 400 by 400. So that way it is only able to detect the features in one scale. Whereas Laplacian of Gaussian, what it does is like it will take the image into 5 different scales or 7 different scales, depending on the kind of algorithm we have, and it computes the Laplacian in both x and y axis to compute or sigma. Like we have different Gaussian outputs here, and then like we try to obtain the maxima in all the 5 scales, and accordingly determine when is the where is the feature. So but however, it's not that tricky, but it's, yes, it's a little difficult to implement if we go try to do it all on our own. And then there is something called as difference of Gaussian, like a small derivative of what we discussed previous, like Laplacian of Gaussian. It is, what it does is like it takes a difference of 2 different scales of images, and we try to find extremum in that particular filter, or in that those particular output of this Laplacian's difference. Then we have something called as SIFT. SIFT is actually a further derivative of Laplacian difference of Gaussians, and it is very popular. Like anybody who is working in the image processing field would be knowing that SIFT is very popularly used. Like it was like in 1980s. No, I guess it was in 2004. In 2004, Lowy actually proposed this technique of SIFT. So SIFT is basically completely what is that? It provides a 128 element vector actually for each feature point. So if suppose you have suppose if you have a point here, and if we compute a SIFT detector here, what it will do is it will take a window of 4 by 4. It will take a window of approximately 15 by 15 size of image, and it will compute the histogram of the
Can be
orientation and
reduced.
magnitude
2
of the
loop
gradient in all the directions. And then it will
degrees to
compute a 4
smooth
by
the
4
DC.
histogram with 8 bins in each of them, and accordingly then
The
create a
rectified
128 element vector. I remember we did try to implement SIFT long back in 2012. Like we tried to implement it as it is, but it was really very difficult to implement. And even after trying very hard, we were not able to completely do that. Like, we were not able to match our results of SIFT with already existing. Eventually, we came to know that SIFT is a patented technique and it cannot be used for any commercial applications. So then we moved
and
ahead with
brushes.
SURF. Surf is
Each cycle.
like also you can say is a further derivative of shift technique. It uses the second order derivative of second order Gaussian derivatives and uses Haar wavelet response, and is only a 64 length vector, but is also like I would say provides a very good unique response at every point. We have been using surf very frequently in our research. Other than surf, recently now we have binary descriptors like brisk, brief, orb, so they are also popularly used. What you can feel is like understand is like this. Yeah, like this feature detectors and or descriptors are basically able to provide you a 64 or a 128 length vector for each point. So that way we are able to describe each and every point of an image. However, we do not need to do with each and every point. We only do it with those specific points which seem to be having a good corner response, or those points which seem to be unique. So first we do a detection, and then we do a description by taking out a feature vector, and then we do a matching. Now what a feature matching is, there can be different techniques of feature matching. Now you can imagine you have a 64 length vector, and on the other side you have some hundreds of 64 length vector. So you can, one technique is like, in order to match one feature with the other, you can take this feature and do a like subtraction or a multiplication, and whenever we with each of the feature on the other side. That's an exhaustive search.
Thing.
Sorry, has anybody anything to say? No, I guess. Then we have the second technique is hashing. In hashing, what we do is like we try to create a small descriptor of this big descriptors, and we use them to hash them. Like it's a very good technique in order to um, like represent something in the short form, and then we can use this to like compare the vectors. And the third technique is like nearest neighbor techniques, and like there are, like you can compute the absolute difference, or like sum of square distance, in order to calculate which feature matches with which one. So now until here, I guess we have discussed good detail of what are the basic elements which are required in order to have a vision based navigation. Now, what's a vision-based navigation is like, you imagine you have a camera, or you have augmented reality glasses, and if you go 5 steps forward, the uh, augmented reality glasses can tell you you have moved by 5 meter in x-axis, 2 meter by y-axis, and if you have moved on the z-axis, yes, if you have done like if you have moved a slope, and also you can tell you how much in which direction you have moved. So this kind of things are very, very useful in different applications, which I'll come across. So now navigation has evolved from an astrolabe to celestial navigation. Celestial navigation, like using star cameras in order to obtain where we are in the space, and then uses of magnetic compass, inertial sensors, and eventually presently GPS or GLONASS. These are used popularly in different applications. In order to represent the orientation, either Euler angles are used, or a quaternion directional cosine. While I was working with in India, I was working with Euler angles. After coming back here, the professor, first thing that the professor told me, that you have to work with the quaternions and not with Euler angle. So that was the first major step when I came here and started working. Euler angles has its own disadvantages, but quaternion has its own. The only disadvantage that I found with quaternion was that it is very, very difficult to follow. But it's okay, you have to. So now vision based navigation is like, you can, yeah, on your there are two images now in front of your screen. The first on your left is a humanoid robot, and the second on your right is your Mars opportunity rover. So the two eyes of a humanoid robot is a stereo camera, and the two eyes, or the two cameras that you see over a Mars opportunity rover over here, is also a stereo camera. Now, why do we need a stereo camera? It basically tries to give you a depth output at every time. And what it does, it tries to obtain the rotation and translation of uh, how a rover or how a humanoid robot is moving in the direction or in any direction. So when suppose when you go when a satellite or when a rover kind of thing goes in a place where there is no GPS, so what does it do? It does have inertial sensors, but they need those inertial sensors like accelerometer, gyros, and magnetometer. They need external aiding. Generally, when we navigate on the earth, we have GPS, or like, but when we go underground or when we go underwater or in mines, we do not have GPS signals. So what do we need? We need some external aiding, and vision is a very good source of vision, aiding. And since in 2006, in 2006 NASA launched Mars Opportunity Rover, and since 2008, you will see that there is a huge flood of research in this area. And I'll show you the applications at the end. You'll find that these applications can be hugely used in different things and different walks of life. So vision-based navigation is a process of determining the position and orientation of a robot by analyzing these camera images. And now what analysis is done, I'll discuss with you in detail. So now this is just an image of an aircraft to show you what is a roll axis, pitch axis, and a yaw axis. So roll is basically, this is the x direction of the aircraft, and if you have any movement or any orientation movement in this direction about this axis, it's a roll axis. About a perpendicular to this is the pitch axis or the y-axis on the wing side, and a perpendicular to both the axis, z-axis, is the y-axis. So this same principle of orientation is used even in a quadcopter or a like any moving vehicle in that sense, I would say. So the same principle have been used in our research as well. So now before that, why vision-based navigation is actually needed? So this slide has been taken from from one of the pioneers in this research area, as David Scaramuza. He is in ETH Zurich, and he has actually pioneered this research in the area of vision-based navigation. So vision-based navigation is used because if we just there are something called as wheel odometry in the wheels of any vehicle, but those are actually prone to slippage and do not provide very accurate output when we have such adverse weather conditions. Similar, and other than that, wheel can be used as a complement to GPS, inertial sensors, or laser odometry. Whether in a GPS denied environment such as underwater and aerial, view has very good importance. Like now, in after some time, I'll say you that the vision-based navigation is also coined as visual odometry. It was coined in 2004 by Nestor, and since then it has been very popularly used in the literature in that way. Now, before that, now we'll discuss what is an abipolar geometry and fundamental matrix, which is actually the fundamental of the whole computer vision and vision-based navigation task. So here, suppose you can imagine a 3D point here, capital X, and you have two small points X and X dash. So when we have a stereo camera, we have two different camera centers C and C dash. And so every point X is related to X dash through a matrix H pi. This H pi is basically, you can say, a homogeneous transformation from X to X dash through a epipolar plane. And any point x dash will always lie in a epipolar line. So when we have something, 2 points lying on the same line, we can always relate it as e dash cross xx. And then we evolve something called as fundamental matrix F here, and x dash can be written as h pi x, and l dash, which is the line connecting e dash and x dash, as f into x. I know this, like I took like around some few like 2 or 3 days to understand this. It will be difficult for you to understand in just one go, but yes, for your like information purpose, you can just understand that X in one image is related to X dash in the other image through a matrix called as F as of now. Now, this is the case when we have two images from the stereo camera. Now, suppose we have the two images from the stereo camera represented here, 1, 2, 3, 4, 5, 6, 7, 8. So on the left is the images through the left camera, on the right is the images through right camera. I guess this image is not visible. Leave it, it's okay. So now, on the left, we have the image sequences. On the right, we have the camera trajectory or the vehicle trajectory on which this camera has been mounted. And what it yields is it yields the rotation matrix in all the three directions at every time, and the translation in all three directions at every time. This is the output of a vision-based navigation scheme. And this is a brief pipeline of how a vision-based navigation or a visual odometry actually works. The first is an image sequence. Then it is feature detection, then a matching, a ransack-based 3D motion estimation, post-concatenation. We will go in detail with each of them. Capturing image sequences like this. Like if you have on the first time, like as soon as you switch on the camera and you have the images coming in, when you switch on the visual odometry pipeline, it will take the first two images of the camera, then it will take the another two images of the camera, and then the next four images, the next two left, two right. So you can also see here on this side how the images have been captured. So this is a part of capturing the image sequence. Now what it does, it always considers the images at two different time instant, that is t and t minus 1. So what we do is first is we detect the features. I hope you can see these yellow dots here. These are the features which have been detected in the image. You can use any of the features like shift, surf, or brisk, but it has to be a scale independent or like a multi-scale detector, because many times, suppose as we move further, a car which seemed to be small earlier, that actually gets bigger over as the car keeps moving, or anything which is seen by the camera which is mounted on a vehicle will have a size change over time. In order to incorporate that size change in the feature in the algorithm, we need to have multi-scale detectors. The reason for that is you can understand that we have whenever we mount anything or a camera on a vehicle, things keep moving, and as things keep moving, the size changes, and in order to compensate the size change, we have this multi-scale detectors. Now when we have detected the features, we will do a intra-frame matching, that is matching the features from left to right and both the sides. Now when we match these features intra-frame, we then do an inter-frame matching. That is, what are those features which are existent in all the four images of like left, right, and the top down. The headlight of one car should match with the similar car on the other side. But many times these there are noises, there are errors. So we apply different constraints like motion constraint, abipolar constraint, and using this constraint we are able to remove the outliers. And you'll see in the next that we have removed some of the outliers, and the red color feature match which seemed to be erroneously matched from a, like you can say, from instead of base of a tree it was matched to the top of a tree. So it was a outlier. So using algorithms it has been removed, and then once we have this set of images, we can consider these features to be our starting point from where we can actually compute our motion. So these are then sent to a ransack based 3D motion estimation. Now, small like taking a off route, we'll just give a brief overview of how a ransack works. If somebody has worked on k-means clustering, you will find it somewhat related. So this is a ransack. What the importance of ransack is, it helps in removing or it helps in obtaining the most suitable motion or most suitable path for a most suitable line for any points. Like I'll show you in the example how that works is, so imagine you have a cluster of points, and you select 2 points. So the target of this particular example is to show how you can obtain the most fitting line for this particular for all the lines pointed here or provided here. So you select a sample of 2 random points and you create a line out of it. You need only 2 points in order to make a line. And then what you do is like you try to find a distance from all the points to this line and calculate that. Second, what we do is like this is the point of calculating distance from this line to all the points and use this as a error measure. Second, what we do is like we try to find that how many points are within a particular range of these points, like how many are lying within a threshold level of this line. That's those are called inliers, the green lines, the green dots that you see here. Then we take another 2 points and do the same thing. Then we take another 2 points, do the same thing. And then we take another 2 points and do the same thing. Now you see in this case, when the points are lying close to the point of line, uh, then there are maximum inliers. And the line which has a maximum inlier is considered as the output of this particular ransack. So for a ransack to work nicely, we need to have n number of iterations. That is, if we have 2 points, we need to have this many iterations. There is a specific formula for this, and this is that formula which you are saying right now in front of the screen. So we consider probability of success as 99%, percentage of outliers in the data to be 50%, and then we have n is equal to 145 for a number of points as s. S is equal to 5 here. Now, you may see that rotation R has 3 degrees of freedom, translation T has 3 degrees of freedom, total is 6 degrees of freedom. So so each and every time, what we need to do is, you can imagine you have some set of points on your left, on your on your left side of equation, and set of points on right side of the equation, and you have an unknown R and T. So what we need to do is, we need to find that appropriate R and T which can actually relate the points from the left to the right. So once we obtain that R and T, like we use ransack for that, what we do is like we concatenate them. So if you have something on your left, we keep concatenating from ck minus 1 to ck plus 1. And once we are done, we have an output something similar to this. So in the Jiffy here, you can see as the vehicle is moving, the trajectory keeps moving up. And this particular information is very, very useful. The current image that you are, current GIF that you are seeing here is with the help of a vehicle, with the help of a camera mounted on a car. And this data set is from Kitty, that is Karlsruhe University, Germany, and they have done a good research in this area of autonomous vehicles. And these data sets are freely available for to use. We have used this data set many a times, and it's like, I can say, the base point for starting this research work. And this is a portable vision-based navigation that we developed in our lab, and it was through a DRDO funding agency. We were able to capture some data sets. This is the stereo camera mounted here. Earlier we kept our controller board on the small robot, but then we were able to develop a small package in which everything was put, and we could develop as the vehicle keeps moving, we were able to develop the trajectories, which was very, I would say, better as we kept moving further in the research. However, that is currently, as of now, standing at that point. Need to take it forward after I come back. And now some of the reported research in this area. So it's like so the first thing that we did was descriptor length reduction using low variance filter for visual odometry. In this work was done along with one of my students, Srijay. And in this, what we did is, if suppose you consider that you have 64 length vector, the idea was to reduce this length of vector but still keep the accuracy to be same. So what we did is we proposed two different techniques here. The first one was randomly removing some of the feature indices. So if suppose you have 64 length, we removed like around 40 indices out of it, and showed that randomly that even if you have 24 or a 20 length of feature vector, the accuracy is still the same, because these feature vectors are actually very unique, and they're so very unique that even if you remove some 44 or 40 random indices of the feature, it will still have the similar accuracy or a similar matching accuracy specifically. The second work of this same thing was like we removed the indices based on the variance, that those particular indices which do not have good variance, they may be removed, and only those which have a good variance may be kept. So that way we were able to keep the information content in the descriptor still to be the similar and obtain a similar accuracy. We're able to reduce the total time taken. Actually, feature descriptor, as long feature descriptor you have, more is the time you take for matching. So that we were able to reduce the computational time of matching. These are some of the results with that. Here, like these are the different trajectories. I showed you one trajectory in the ZIF image, how the trajectory is calculated. This is that particular trajectory, and it's, I think, data set number 3. And then you have a few more data sets. Actually, Kitty provides you 11 training data sets and 10 test sequences. We worked on the training sequences because we were not working on the neural network on that at that time. So then this is one of the latest research that has been published with like it has been published with International Journal of Robotics and Intelligent Systems. Yeah, Springer. So it's the MIVO. MIVO work. What it does is like it's you can say it's an extended version of what we did initially. Of this work has been done with one of the PhD students who was working with us in the lab, and it's his PhD work actually. But I'm presenting here as a part of, because I was partnering here with that work. And in this, what we did is like we have some images sequences, we do a similar feature detection, and then we apply different epiprolar constraint. One like good or unique thing here was disparity based binning. That means we have different features, and based on the features we can also compute its depth. If you know its correspondence in the other image, like there is something called as fb by d, or that formula is like if you know the baseline distance between two cameras, and if you know the focal length of the image, and if you can compute the difference between the location of two different features in two images, we can compute its depth. And so those features which were far away were kept in another bin. Those features which were near were kept in another bin. And these features were then sent to a MI computation. And what it does is like it computes the mutual information between all the features. So those features which seem to be similar to each other were not sent further for processing. So imagine you have 100 features in which a few of the features seem to be similar. So suppose you have a hilltop, and on those hilltop you have two features. You need not keep the two features because they might both be the same. So depending on this mutual information computation, we were able to reduce the total amount taken by the whole visual odometry algorithm. This algorithm was applied on Kitty dataset, which is like this is the setup of a Kitty dataset in which a Verodyne laser scanner, two point gray cameras are kept on the camera above the car, and on the right of your is like Europe MAV camera dataset capturing system. It uses a MAV mounted on, and the camera is mounted on top of it. You can see here S camera 0, and then you have S camera 1. These are the two cameras on this quadcopter. This dataset has been also or is being used widely in this research area. And some of the results of MIBO are like this, that we were able to reduce that, like we were able to in fact keep the translation error to be similar to what it was for different sequences. And then as compared to the normal VO here is like the one without mutual information computation is takes much, like if you compare it with the scale of 1, takes 1, then the other ones like the one with MIVO ransack or MIVO inertia takes a lower time as compared to this one. I'll not go into details of MIVO, ransack MIVO inertia. That might not be the right thing to do here. That's not research presentation for that. So, and then these are the output of Euroc MAV. These are the three different trajectories, and you can see that the dotted line is the ground truth, and the one which is shown in green and the other one is also in blue are the output of MIVO and standard VO. Then we have the another research as inertia constrained visual odometry. In this work, what is done is like we have some inertia at every time. So this concept was used here in this. What was hypothesized was like if a car is moving into with a speed of 2 meter per second, or like whatever be the speed, so it will not suddenly change from that particular speed. So if we keep if we apply the similar kind of motion on the t-1 features, we will predict where our features would be in the next time instance. So based on this prediction, those features which used to follow the predictions were only sent further for processing, and those that do not follow the prediction, they were not sent. So this way we were able to apply inertia constraint, and the output of inertia constraint visual odometry showed us that yeah, this can actually be used for estimation of like rotation and translation. The other part that we explored further in this was like if suppose you have a car coming at some other speed from the other direction, you can also detect that because that will follow another motion and not an inertia motion. So this research had twofold results. One was like estimation of our own vehicle output or rotation and translation, also estimating the rotation translation of other vehicle. This is the recent research in this area, that is joint forward backward visual odometry. In this, what was done is like we estimated output. We estimated the visual odometry output from a left to right in a front way direction. That is from t to t-1, and the other one was from t-1 to t. What we found that these algorithms are very specific to how emotion has been captured. When we go from t to t-1, the features from the far end side actually provides us a good estimate of rotation. Whereas when we go from t-1 to t, the features on the near end actually provide us a good estimation of rotation. So that way, when we were able to combine both the output, we were able to see that we obtained a good result on joint forward backward visual odometry. And this research was published with an international conferences. And then we have recently we also did some work on deep visual odometry. You see like everywhere now, everywhere you see is like artificial intelligence, though that's I think is highly misnomer. Not very much required to have artificial intelligence in everything, but still, so like we have to go with the bend. So in the deep visual odometry here, this is the convolutional neural network CNN part, in which the CNN was used to obtain the rotation and translation using the input as images. This was the RNN, and this was the autoencoder. I won't be able to delve much details of this because I myself knowing very less about this research. And this has been done with one of my colleagues, and I was partnering in it for the estimation part alone. And this was the research work here, that instead of estimating all the rotation and translation together, rotation of all three axes and translation of all three axes was estimated separately, and this showed that this actually improves the accuracy. One of the hypotheses that we had in this was we did not we felt that the rotation in all three directions are actually mutually exclusive, and like they are not interdependent, so why to estimate them together? And this actually helped us because in understanding that the rotation parameters can be learned separately and obtain a better estimate. Optical flow was used here for training this neural network here. And then lastly, like we had a book chapter on motion estimation, in which we discussed about the evolution and trends in visual odometry. It was discussed in two separate parts. One was learning based framework, and other in non-learning based framework. In the learning based framework, we have image training sequences in which the image can be trained or the neural network can be trained either using optical flow or a raw pixel or a classified feature or a synchrony detection. Based on the training network output, we could estimate either the depth or a motion parameter or a ground or we can estimate other estimate the ground as in like if there is any movement at the ground, if whether the ground on which the vehicle is moving, if that is fine or not. So, and then the feature and area based framework. So my research work has mainly been focused only on feature based research. Area based research is still like is a good area of research, but is mainly used for depth estimation. So we have feature detection and matching. We do a feature selection, like Mevo, and those things are like feature selection framework. There are different constraints that are used for removing the outliers, and then we have motion estimation and post concatenation. After post concatenation, there's also a technique of bundle adjustment or local optimization. That is, if suppose we started from point X, when we complete a trajectory, we should always be able to read that particular point X if we are following a closed loop circle. And that way we are able to also do a refinement in the pose. And the second part is in the area of area based techniques, in which we do a reason or template based matching. And we can also do global image descriptors, and that's another line of research here. And then after doing plane fitting, then we obtain the motion and do a post concatenation. I'm now nearing towards the end of my presentation. That is, we have the research that I showed you until now, or the basics that I followed until now, whatever is like was of visual odometry. Now, this is the current research which I am doing right now here. It is the visual inertial odometry. In this, what we do is we take the output from vision-based navigation, the output from inertial-based navigation, and combine them together in a EKF framework to obtain a visual inertial odometry. So visual inertial odometry is the actual thing that is used in principle in different applications, because vision-based navigation alone on its own is not very accurate. An inertial sensor on its own is also not very accurate, but a fusion of them is actually providing a very accurate and reliable output. And this is basically the similar feature-based motion estimation pipeline. I'm not gone into the detail of inertial navigation system or their pipeline, because I have worked with the inertial sensors and like attitude estimation and pose estimation with help of inertial sensors, but that's a completely different line of research. So we'll not touch that over here. So the output from the camera, the inertial sensors, and also sometimes GPS can be fused together to provide the states, that is pose and biases at every time instance. And then with a brief of different applications of vision-based navigation. So vision-based navigation can be used in unmanned or autonomous vehicle navigation. It can be used in robotic surgery. It is used in augmented reality. Because if suppose you take a movement of your eye by left or a head by left, you should know that your head has moved by this angle, and accordingly your display should also move in that angle. Then you have a satellite to satellite or aircraft to aircraft docking. Aircraft to else, you would have seen some of the videos in when we have big buildings, urban canyons, we do not have access to GPS signals. So those are the places where we actually need vision-based navigation, and it is actually used there. And then, so with this, I will thank each and everyone for listening to me patiently. Uh, and I hope I was able to do some justice to your time, but I'll be now open to questions so that we can discuss if there is anything.
So thank you, Sasi. So, dear participants, if you have any question, you can discuss it now, or just put it in the chat box and we can discuss it. So one question from my side, Sachin. So for estimation, you are using EKF, the extended Kalman filter,
Yeah.
because the model is non-linear or something, or other methods of estimation like normal
Uh,
Kalman or UKF, those have been
no,
tried.
yeah, like actually EKF is not used for vision-based navigation here. We are using the Kalman filter here only for fusing the estimates from vision and the camera. So generally EKF, the extended Kalman filter, we have the non-linear model. But yeah, it's like there are research in which UKF or other forms of Kalman filter are also used. And it's like an ongoing research, you can say, in which still people keep seeing what other or better optimal estimation technique can be used.
Yes.
Yeah. So I is anybody having any question related to like feature detection and matching? But yeah, I would say that this is a very evolving research, and like in India, we do not see much of research in this area. But I would say that in future there will be research in this area because everything in robotics or anything you go ahead with autonomous operations, you need to have the vision-based systems. Even if not vision-based, even if you take up any sensors like lidar or radar, if they are used for navigation or any purpose, they need to go through a similar kind of processing. So if you have some questions, I would be happy to suggest. Is there anything about automation aeronautics that replaces a pilot? Well, I know that there are pilot training programs, or like mm, there are systems in which a pilot can, how to say, pilot simulation systems, in which what they do is like they already have this kind of synthetic synthetic environment in which a pilot can be trained, or a person who wants to be a pilot, he can be trained. Automatic pilot is, or autopilots are used in, you can say, is kind of an autonomous or unmanned vehicle. When you have an unmanned vehicle, it's like an autonomous vehicle without a pilot. It all works on the basis of information that you have. But as such, I'm not aware of anything in the real world in which a person is an autonomous vehicle is flying without somebody in it, and pilot is always there. But yeah, that's there as a future vision, that there will not be a pilot, but like similar to self-driving cars, there will be self-driving aircrafts as well. And yes, this research is completely related to automation in aeronautics, because vision-based navigation is was actually evolved for Mars rover initially, and it is from there on that this particular research has taken next step forward in different directions. So I hope I am able to answer that question. Okay.
Yes, yes.
Yeah. Anybody else, like if anybody has any doubt related to anything in the presentation, can please tell me. I might try to like keep that as a feedback so that I improve myself next time.
Uh, for the feature detection, do you have any kind of thumb rule, like how many features do you generally pick? Because this is a kind of pattern recognition problem.
Actually, feature detectors have something called as a threshold, actually. So if you tune that threshold, you can decide you want more feature or you want less features. It's like um, if you have like if you consider that there is a scale from 0 to 1, so depending on the processing speed, or if you have a if you know that yes, you want to have only 100 features in your system, you can tune your threshold accordingly. Because many a time, depending on the kind of image, the same threshold not may not work on all the different kinds of images. Like I mean to say, same kind of camera, all cameras have different noise levels.
Yes, so it depends on the type of sensors as
Yeah,
well
it
as
depends. And as well as in the application and the processor that you have. Suppose you have a processor which can only process up to 50 features at a time, so you will tune your threshold accordingly.
okay, okay. So one question I can see in the chat box: any work in the vision-based navigation assistant for visually handicapped people?
Oh, yeah, that is a very nice research area. And in fact, I have personally proposed that research when I came here as a Fulbright fellow. Like, it's like a blind guided system. A visually assistant is like, if you can imagine somebody as a blind person, he can be assistant with this kind of system. There are research in this area as well. So if suppose a person who is blind wants to move in a direction of like 2 meters in the left and on a particular point, so with the help of the system, you can guide him from going from one place to the other. And this is a futuristic, I would not say futuristic research, but this is a research going on with the current, with these principles of vision-based navigation. The principle is completely same. It's just that it has to be taken down to some other algorithms, and everything is purely same. It just has to be taken and put down into a blind vision navigation, a blind guidance system.
Yes, Sasi. So I think we are more or less
I think
addressed
somebody
all.
needs a feedback link. I do not know about that.
And okay. So thank you so much, Sasi, for getting into trouble of
No,
waking
it's
up
completely fine.
effectively. We can have we had a very good session on the feature detection and feature matching, feature selection, and
Yeah.
all those vision aided inertial navigation projects you have explained so far.
Yeah, I'm also
So
sharing my email ID with everyone, like in the chat box. If suppose somebody has any doubts, or if like somebody wants to discuss further research in this direction, I'd be more than happy to discuss. Like in future, I would like we would like to do more research. I see that there are participants from all across the country here, so I would really love to have more research discussions with people from across the country. And if somebody has some good research, we can surely collaborate on that. So looking forward to that actually.
yes, yes, even we have participants outside India as well, so
Oh,
across
that's
the globe.
nice. Hmm.
So we will share the materials as well as your contact details with everyone so that they
Sure,
can,
sure.
in case of any further
Yeah,
collaboration.
yeah, sure, sure.
Uh, okay, then I think there is no more questions from participant side as of now.
Yeah,
So we can wrap up the session for today. And thank you once again, Sasi, for
yeah,
having
sure.
part of this
Thank you
program.
very much, participants, for actually listening. I was not sure whether I was able to like deliver what was expected out of me. But if you have any doubt, please feel free to drop me an email. I will surely reply each of them.
Thank you, thank you. And
Yeah,
all the participants, thank you so much for listening actively. And we'll have our next session tomorrow at 11:30 a.m. And for now, we will just close the session and have a good day, Sasi, and all the
yeah.
participants.
Same to you. Thank you.
Thank you.